Increasing the number of resistors in parallel in a circuit will decrease the total resistance of the circuit. Let's see how this works by comparing two circuits. On the left, we have a simple series circuit with only one resistor. Let's assume the resistance of this is some large value R, meaning there is a high total resistance in this circuit. Then on the right, we have two of these resistors in parallel, so they both also have a resistance of R. So if there are two resistors, you would think that the total resistance in the circuit, in other words the combined resistance of these parallel resistors, would be larger than the series circuit. But actually, there is a lower total resistance. You won't be expected to calculate this total resistance for your exams, but you need to remember that adding resistors in parallel will decrease this total. But how would this affect the properties of the circuit? Well, increasing the number of resistors in parallel in a circuit will increase the total current in it. Let's see how this works with two more circuits, where instead of resistors, we're using lamps. In both, we have a cell which will have the same potential difference of V, and then we'll assume each lamp has the same resistance R. So how would the total current in each circuit compare? Well, remember that we relate the current, resistance, and potential difference for a component with the equation V equals I times R. And we can also apply this equation to the total values for the circuit. So in the parallel circuit, we'll have the same total potential difference, since this is just the potential difference supplied by the cell. Then, as we've just learnt, the fact that we have two components in parallel means there is a lower total resistance than there would be with just one component. So this means there must be a higher total current in the circuit in order for there to be the same total potential difference. Again, you'd expect the current to decrease as we add more components, but it actually increases. This might be a little hard to understand without knowing what this new current is. So let's take a closer look at what's happening. We'll do this by identifying the potential difference across each component and the current through it. On the left, there's only one component, so this must have the same potential difference as the cell. Then we'd use the equation V equals IR to determine its current I. Then on the right, both lamps are in parallel, so they will have the same potential difference across them. This will also be V, as there are no other components besides these lamps and the cell. Then we already know that they have the same resistance, so we can use V equals IR again to determine their current. What we've shown is that all three of these lamps have the same current flowing through them. Also, the parallel lamps would have the same brightness as the single lamp, which will be true no matter how many more parallel lamps we add. But how does this affect the total current? Well, remember that in a circuit, the current starts flowing from one end of the battery and will split down the two branches. Then they'll join back together before repeating the cycle. In other words, we can determine the total current by figuring out how big it is when the two smaller currents add together. So we have two currents of I adding together, making a total current of 2I. Now, you won't need to be able to recall this detailed explanation for your exam, but you should be able to understand that since the total resistance is decreasing as we add components in parallel, the total current must be increasing. But how else do parallel components affect the current? Well, the current is split between parallel branches in a circuit depending on the resistance on each branch. In this circuit, we have a lamp and a resistor on parallel branches. The lamp has a resistance of 1 ohm, while the resistor has a resistance of 6 ohms. So since this bottom branch has the higher resistance, it will also have the lower current flowing through it. In fact, the greater the resistance of a branch, the lower the share of current it will get. Often, parallel circuits will use resistors like this to adjust how currents are split between their branches. But why is there a lower current in the bottom branch? Well, let's suppose we're using a 12-volt cell to power the circuit. This means the potential difference across the lamp will be 12 volts, as will the potential difference across the resistor. Then, using V equals IR again, we can determine that when the current splits, we'll have 12 amperes in the middle branch and 2 in the bottom. Notice that the resistance is 6 times larger in the bottom branch, but the current is 6 times larger in the middle branch. But what about when we have a parallel branch with no components? If a branch of a circuit has no components, then almost all the current will travel down this branch. So let's consider this circuit, where one branch has a lamp, let's say with a resistance of 2 ohms, and an open switch on the other. So initially, the current cannot travel down this branch, and only travels along the bottom branch, and we'll see the lamp light up. For your exams, you could be given a circuit like this and be asked to describe what would happen when we close the switch. Well, this means a current can now flow along this middle branch as well, meaning it is being split at this junction. But we have no components on this branch with notable resistance. So the total resistance of the branch is almost 0. All there is the small amount of resistance of the wires. Then in parallel branches, the smaller the resistance, the greater the share of current it will get. So if this branch has almost no resistance, it will get almost all of the current. This would then mean there is almost no current in the bottom branch. So we would likely see the lamp stop glowing once we close the switch.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!